Hi, good evening, all. First of all, thank you all for choosing to attend the December edition of Kaapi with Curiosity. I'll ask the director to give you the welcome address.
Dear friends, good afternoon to all of you, and respected Professor Rahul Nandkishore, Professor Bhattacharji, and the ladies and gentlemen here. Welcome to yet another lecture in the Kaapi with Curiosity series, which is being jointly hosted by JNP and ICTS. All of you know very well. And today we have yet another interesting topic. That's what I was telling somebody. Today we are fortunate to have Professor Rahul Nandkishore from Boulder, Colorado, a professor from there, and he's speaking on new frontiers for statistical physics. I was thinking new frontiers in statistical physics. Now it connotes something else, new frontiers for statistical physics. So nice. And anyway, Professor Bhattacharji is going to introduce the speaker today. So thank you very much. Enjoy once again. On behalf of both JNP and ICTS, I welcome you all to this lecture. Thank you very much.
Thank you. So, hi, welcome everyone, and I'm sorry for the slight delay in starting, but I have the great pleasure of introducing Rahul Nandkishore, professor from UC Colorado Boulder, giving us a talk today. He's actually visiting ICTS as a part of a conference that's going to start from tomorrow. And so, Rahul, I've followed his work for over the last decade or so, and he has been at the forefronts of various things that has been happening in one of the most interesting areas of physics, which goes under the name of many-body physics, and it really encompasses a huge amount of things that we hear and over a large variety of systems, starting from quantum many-body physics to biological systems, etc. And Rahul has been working on a diverse set of problems in this area and has been contributing at the forefronts, and he would be sharing some of those fantastic things that have been happening in the area. So let me just tell you a few more things about Rahul. He graduated from MIT in 2012 and then was a postdoctoral fellow at Princeton for till 2015, and then moved over to UC Boulder, and where he's now a professor and the director for Center for Theory of Condensed Matter. Rahul's research has been recognized in various forms. He has received the Young Investigator Award from the US Department of Defense, and the Sloan Fellowship, as well as the Simons Fellowship. And he would be talking about the wide array of things that he has been doing. So, Rahul. Thank you. Oh. Yeah, 5. Okay, but before he starts, let me hand him over a small memento on behalf of ICTS. So, thank you.
Okay, it's great to be here. Maybe just for calibration, could I ask how many people here have seen Newton's laws? Just raise your hands. Laws of thermodynamics? Schrodinger's equation? Okay, yeah, okay, it's useful. Okay, so today I'm going to be talking about new frontiers for statistical physics and some new developments in statistical physics. I should say that perforce this is just one talk and a brief overview talk on a lot of new developments. Now, if you really want to know more about statistical physics and about some of what's been going on, I will do a little self-advertisement. So I have this course on Coursera, which you can go look up, and that has a lot of lectures aimed at more or less beginners introducing condensed matter physics. But now, let's begin. So, new frontiers for statistical physics, but why do statistical physics in the first place? So let me start by observing that everything on Earth is governed by the known laws of physics. Yeah, like maybe the questions of quantum mechanics and black holes are still open and unsolved, and we don't know how the physics of black holes works. But there's no black holes on planet Earth. So Schrodinger's equation governs everything from this table to this laptop, you, me, the air in the room. All of these things are governed by laws of physics that we already know, by equations that we know how to write down. Yeah. So in principle, if we could just solve Schrodinger's equation, we would be done. I could predict exactly what you'll do next. I could predict what will happen next in politics, stock market, whatever. Everything should follow deterministically from underlying physical equations. But of course, this cannot actually be done. Yeah. Firstly, it cannot be done because the world is complicated. So in any macroscopic object, there are Avogadro's number of degrees of freedom, and how are you actually going to solve the underlying equations for Avogadro's number of degrees of freedom? If you do undergraduate physics, you learn how to solve the two-body problem, and you already learned that the three-body problem is unsolvable analytically. So if you can't even do the three-particle problem, how are we going to do the 10 to the 23 particle problem? And now you could say, okay, well, we'll give up on sort of exact analytic pen and paper solution. Instead, we'll just go simulate the problem. Okay, current state of the art for how big a system we can simulate is about 40 particles. So 10 to the 23 is still a long way away. Maybe we'll wait until computers get faster. Well, okay, the difficulty of the problem is exponential in the number of particles. So even if Moore's law continues forever, then next year we'll be able to do 41, and the year after that 42, and the year after that 43. But to get up to 10 to the 23 will take a very long time. Yeah. So that's one sort of practical objection of, even if we know the underlying equations of motion governing the behavior of every atom, that doesn't mean we can actually explain what macroscopic objects like you and me are going to do. Yeah? Another maybe more conceptual problem is, suppose you had like a magic computer and it could just solve the equations of motion. Yeah? And it gave you the solution. Here's the solution to the equations of motion for 10 to the 23 particles. What will you do with that solution? Where is the insight? Where is the human comprehension in that solution? And at the end of the day, we don't just want the solution to an equation. We actually want some understanding. We want some human insight. Yeah? So the equations cannot be solved practically, and even if they could, the solution would not really yield any insight. So to actually get insight and understanding, we need new approaches. And those new approaches is what statistical physics is designed to provide. Yeah? So the idea here is that in some sense, having Avogadro's number of degrees of freedom is actually easier than having just 3. Because when you have a vast number of degrees of freedom, you just abandon the attempt to describe what each and every particle is doing. Yeah? So if we want to describe the air in this room, let's say, then I don't try and describe the air in the room in terms of writing down a description for every single nitrogen, oxygen, molecule in the air and describing exactly where it is and in what direction it's moving. Instead, I just characterize it by saying, okay, what's the temperature of the air? What's the pressure of the air? Maybe, is there some wind? And have a sort of more coarse-grained description, a more statistical description of what's going on. And in the course of the past 150 years, statistical physics has been built into this very rich discipline with a lot of predictive power for systems with Avogadro's number of degrees of freedom. Yes? If you have questions at any point, just raise your hand. We can take questions as the talk goes along. Yeah, it's good to have things be interactive. Another sort of conceptual cool thing that comes up when you start doing statistical physics is you discover that there are such things as emergent phenomena. So this was sort of encapsulated by the slogan, "More is different," coined by Phil Anderson in 1972. And the idea here is that when you have a large number of degrees of freedom all interacting together, this can give rise to new properties and new behaviors which are not inherent in the behavior of any single atom or particle. Yeah? So you have a lump of metal. and you cool it down, and it becomes a superconductor. And the superconductor is some kind of property of the collective system, but you could solve the underlying equations of motion for single electrons until you're blue in the face, and you would never find superconductivity. Yeah? It's something that's intrinsically collective and intrinsically emergent. It comes only when you have a lot of different electrons all interacting together, and this can give rise to something like superconductivity. So there's many emergent phenomena. I mentioned superconductivity, but by now there's a large universe of possible collective phenomena that can arise when you have complex systems with many degrees of freedom all interacting together. Yeah. Okay. Now, one foundational idea in statistical physics goes by the name of thermalization or ergodicity. And to explain what this is about, let me first introduce some terminology. So statistical physicists like to talk about microstates and macrostates. So a microstate contains detailed information about every single degree of freedom in the system. So if the system of interest was the air in the room, then the microstate would be the position and velocity of every single air molecule. Yeah? If the system of interest was me, then the microstate would be the position and velocity of every single atom making up my body. Yeah? Now, obviously, the microstate contains a huge amount of information, and most of this information we don't care about. Yeah? So we don't care where one specific air molecule is moving. We don't really care where one particular carbon atom in my body is moving. What we do care about is more coarse-grained properties like what's my body temperature or what's the pressure of air in the room, and that's the information that's contained in the macrostates. So the macrostates are characterized in terms of the actually measurable properties like the temperature and the pressure and so forth. Yeah? And there's a huge number of different possible microstates all associated with the same macrostate, because you could arrange, let's say, air molecules in lots of different ways and have exactly the same temperature and exactly the same pressure. Yeah? So these would be all sorts of different microstates which correspond to the same macrostate. They're microscopically different, but as far as the actually measurable properties that we can access go, they're the same. There's no difference between them. Yeah? And really what we care about is the macrostates of the system and how the macrostates evolve. And there's the foundational hypothesis, which goes back all the way to Boltzmann in the 19th century, which is the hypothesis of ergodicity. And the ergodic hypothesis essentially says that the system explores over time all of the microstates that are consistent with conservation laws. Yeah? So if I set the system up with, say, a certain amount of energy, then the amount of energy in the system cannot change. Energy is a conserved quantity in physics. But there's lots of different microstates with the same energy, and over time the system will explore all of those different microstates. Yeah? This has consequences. One consequence is that you will spend much more time in macrostates which have a large number of corresponding microstates than in macrostates with a small number of corresponding microstates. Yeah? So I could set this room up with all the air molecules over in that far corner. Yeah? That's one very specific macrostate, which has one associated microstate. Over time, the air molecules will spread through the room, and now we have a macrostate which has lots of different microstates associated to it. Yeah? Because there's lots of different ways in which you could redistribute the air molecules and still have air filling the entire room. It's possible, in principle, that all of the air molecules end up back in the far right corner and we all start choking because we're all sitting in vacuum. But this won't happen in practice because there's only one microstate associated to those macrostates. Yeah? So this is the second law of thermodynamics, the law of increase of entropy, and this law of increase of entropy, second law of thermodynamics, really comes about from this ergodic hypothesis. So it's because the system can explore all of its microstates that you tend to go towards macrostates with more associated microstates, and that means going to systems with higher entropy. Yeah? Now, ergodic hypothesis is a hypothesis. Yeah? It's usually true. And certainly, statistical physics is tremendously successful. So, as a rule of thumb, yeah, this is how systems work. But could it ever be wrong? Could there be settings where ergodicity is broken, where the ergodic hypothesis is in fact false? And yes, there can be, and some of them are in fact very familiar. So window glass, or glass that you could drink your tea out of, that is not an ergodic system, at least not on human timescales. Yeah. So window glass is already a sort of proof of principle example that you can have systems where the ergodic hypothesis is not obeyed, and where you can have behavior which is sort of outside of standard textbook statistical mechanics. Now, this is not a talk about window glass. It's a talk about its quantum mechanical analogs, what I'll call quantum glass. Why? Well, more than one reason. One reason is because the quantum analogs are what I work on, and I don't work on window glass. Also because, remarkably, window glass is still relatively poorly understood, and we have a much better understanding of various types of quantum glass. And also because I'm giving the talk, and this is what I wanted to talk about. So the rest of the talk is going to be about quantum glass, even though we started with window glass. Okay, so we're going to be so we started by talking about statistical physics and concepts of thermalization and ergodicity. Now we're going to be working in the quantum mechanical context. So let me just comment briefly on how these concepts generalize to the quantum setting. So first of all, if we're doing classical physics, then you can talk about the position and velocity of every atom. If you're doing quantum physics, you cannot independently describe both the position and the velocity. This is Heisenberg's uncertainty principle. Instead, information is encoded probabilistically in something called the wave function. So psi here is the quantum mechanical wave function. It contains probabilistic information about the state, and the quantum mechanical wave function evolves in time according to Schrödinger's equation. So what's written down here is Schrödinger's equation, sort of written symbolically, governing the time evolution of the Hamiltonian, of the quantum mechanical wave function. Now, if you open up textbooks on quantum statistical physics, the way the textbooks usually proceed is they say that you have some quantum mechanical system of interest, you couple it to some environment, and then you look at the subsequent time evolution. Yeah? I want to set things up differently. So I want to say that I have a quantum mechanical system of interest, and that's it. It's not coupled to anything else external. Yeah? Now, as a point of principle, you could say that, well, whatever quantum mechanical system you have, it's always going to be coupled to some apparatus, some experimenter, some laboratory. Okay, fine. But your apparatus, your experimenter, your laboratory, they're all also governed by quantum mechanics. Yeah? So treat them as part of the quantum system. You now have a bigger quantum system, which is the system plus the experimental apparatus, the experimenter, the laboratory, whatever. In principle, you could treat the entire universe as a quantum mechanical system and say that this is an isolated system, not coupled to anything else. Yeah? So now let's ask, as a point of principle, we have some isolated quantum mechanical system, time evolving under its own dynamics. Is the ergodic hypothesis obeyed? Yeah? Does standard statistical mechanics apply? And again, as a rule of thumb, it really should, right? Because statistical physics is so successful over the last 150 years, it works so often that it would be very weird if the answer to this question turned out to be no. But could it sometimes be no? Yeah? And that's what today's talk is going to be about. Okay, so let's talk more about equilibration and ergodicity in quantum mechanical systems. So the question is, is the ergodic hypothesis obeyed? Does the sort of internal dynamics of the system bring it to equilibrium in the limit of long times? And now what I'd like to comment is that the process of going to equilibrium is associated with a loss of memory of the initial condition. Yeah? And I can illustrate that with this picture. So here's a coffee cup. We're pouring milk into the coffee. Okay, it's coffee in America. I am in India, so maybe it should be tea. But then again, I'm in Bangalore, so maybe it can still be coffee. We have a coffee cup and we're pouring milk into it, and you set it up with some initial condition where you have some very specific sort of milk swirl pattern in the coffee, and then you wait, and you know what happens if you wait. After you wait a while, it turns into some uniform light brown color, and once it's turned into this uniform light brown color, you no longer know anything about the initial condition. You know how much milk was poured in maybe, but you don't know where, and you don't know what the initial milk swirl pattern was. Yeah? That memory of the initial condition has been erased when the system goes to equilibrium. And you could have set it up and poured the milk in at various different places in the coffee, but once it's gone to equilibrium, you can't tell anymore. That memory has been lost. Yeah? Now, formally, quantum mechanical time evolution preserves all memory of the initial conditions for all times. As a formal statement, information is not destroyed. All information that was there in the beginning remains forever. So now you may say, hang on, there's a problem here, right? How do you go to equilibrium if all information is preserved for all times? And this, by the way, is also a problem in classical mechanics. Yeah? So even for this literal coffee cup, which is not quantum mechanical, this is a completely classical process, you could say, okay, every atom is governed by Newton's laws. I could take Newton's laws of motion, solve the equations, run time in reverse, evolve them backwards, and figure out what my initial condition was. Yeah? Now, the resolution in classical systems is to observe that classical systems are chaotic. So if you really wanted to run the time evolution backwards, you would need to know all the positions and velocities with sort of perfect fidelity, and then you'd need to do an infinitely precise computation running backwards, and even very small errors in your measurements of position and velocity or in your computation would lead to bigger and bigger errors as you ran your time evolution backwards, so you would not actually be able to run time evolution backwards to extract information about the initial condition. Yeah. Now that's the classical resolution, and it comes about because classical mechanics can be nonlinear. Quantum mechanics is in fact linear. Linear systems cannot have chaos in the same sense, so the resolution has to be different in quantum mechanics. The resolution in quantum mechanics is to say that, look, okay, as a matter of principle, the information is all there, but if the only way to extract that information is to measure Avogadro's number of degrees of freedom, that's not something we can actually do. Yeah? The measurements which are actually accessible to us are few body measurements on sort of local degrees of freedom, and so the meaningful question is whether accessible local measurements appear to see a system in thermal equilibrium at long times or no. Yeah? And usually the answer is yes. Yeah? Normally statistical physics works, but today's talk is going to be about settings where the answer can be no. Okay? Questions? Mm-hmm.
Interesting. Perceiving the whole evolution of the universe.
Mm-hmm.
There was a time when the universe was there even before human civilization existed, and the universe will exist after the extinction of human race.
Yeah.
Right. So there should have been an intellect before, and there will be an intellect after. So is it all, how relevant is human perception, how true it is with respect to the dynamics of the universe? So we perceive in a different way.
Yeah.
How we know it is correct? We experiment and we see electricity, we see satellites going, these are all okay.
Yeah.
But there are 90% of things which we are not able to perceive exactly how the universe functions. For example, why the universe created life systems from 4 elements, carbon, hydrogen, oxygen, nitrogen, that protein synthesis. Why it, no. How relevant is humans studies and...
So, this is essentially a philosophical question. Now, of course, we figure out, we do science using the human intellect and using data which is limited by what humans can observe. Of course, we believe that the laws of physics and of science are true regardless of whether we observe them or not. So yes, there was a universe around before humans came on the scene, and we believe the laws of thermodynamics applied, and that it will be around after we're gone, and the laws of thermodynamics will still continue to apply. Yeah? When we could say the same thing about mathematics, like 2 plus 2 is 4, and it was 4 even before there were any humans around to do counting. So, yeah. Yes. Absolutely, yeah.
So, like, what are the conditions for that? I want to ask, like, dynamics of particle, how would they change, and what are the conditions that need to be satisfied in case of, like, what kind of system we are dealing with? So, in those senses.
So I mean, the detailed answer will be different for every system, but let's consider the air in the room as our system of interest. Yeah. So there's one very special microstate where every single air molecule in the room piles up over there. Yeah, and then the rest of the room is in vacuum. That is a microstate. If we look at the subsequent time evolution from there, the air molecules will tend to expand and fill the whole room instead of piling up all in one corner. Yeah. So most macrostates will have, or the macrostate where the air molecules are uniformly distributed through the room is much more likely to happen. And the reason it's much more likely to happen is that there's many, sort of vastly many more ways of arranging the air molecules so that they're uniformly distributed through the room than of piling them, like every single molecule up in that corner. Yeah. So that's one very special microstate. Most microstates don't look like that, and subsequent time evolution from that very special microstate will instead tend to take you to a typical microstate, and a typical microstate corresponds to a macrostate of the type that we actually observe, where we can all breathe, and we don't have to worry about sort of spontaneously finding ourselves in vacuum. Yeah. Yeah.
So when a quantum system interacts with a classical system, the state collapses and so on. So are you saying that you'll get that same behavior by considering the whole system evolving unitarily, and will you get the way people talk about quantum measurements?
Yeah, so I mean, the measurement problem of specifically how do you describe a quantum mechanical system coupled to a classical apparatus, that I am sidestepping by saying there is no classical environment or apparatus. Everything is quantum mechanical, and there is just some big quantum mechanical time evolution, which I am tracking. Yeah. Now, yes, there is a question of interest in quantum foundations, which is really how to go from this completely quantum mechanical description, which really should be the fundamental description of the universe, to the sort of wave function collapse that we actually observe when we interact with macroscopic apparatus. That's off topic from my talk, so I don't want to get into that. Okay. Yeah.
So you had mentioned about the loss of memory of initial conditions. I mean, when we move forward with equilibrium.
Yeah.
So is that applicable only to macro states? Is question one.
Yeah.
And also, since you had mentioned that in a quantum mechanical system, also memory is retained from the beginning of time. So wouldn't that kind of contradict the fact that microstates can retain memory, but when we consider the macrostate, we're not able to extract the same amount of information?
Yeah, so really the macrostate is the only thing we can actually measure, right? We cannot actually measure the microstate because that would involve measuring the position and velocity of every atom, let's say of air in this room. So the statement really is that the equilibrium macrostate has no memory of the initial condition, right? So yes, formally it is true that the time evolution preserves all information about the initial conditions to all times, but it's not part of the macrostate. It's not actually accessible to us. The only way to extract that information would be to make measurements which we cannot do, even in principle, really. Okay.
Sir,
Yeah.
you mentioned that there are few things about glass which we don't understand. Just to summarize, can you say a few things which maybe spark some curiosity?
Sure. I mean, one very basic question about window glass, which is still open, is no. So you have window glass, and certainly on human timescales, it's not ergodic. Yeah. Would window glass at room temperature, would it actually be ergodic if you waited, infinitely long? Right? Is it just that human lifetimes are not long enough? That question itself is not settled.
What would that mean in terms of behavior which we can observe? Because what would that mean in terms of some behavior? Like, I'm not really sure what you mean when you say it is not ergodic.
Yeah, okay. So, maybe a way of answering this would be to say, if you take the viscosity of glass, is it infinite or is it just very large, but still finite? And, in some sense, the question is only sharp if you consider an infinitely large system of glass, right? Because you can't get a true infinity in any finite size system. So if you, consider a pane of glass and you make it bigger and bigger, then in the limit, when this pane of glass is infinitely big, would the viscosity be infinite or not? Yeah, at non-zero at room temperature, and that is a question, the answer to which is still controversial. Maybe we'll take one more and then we continue. Yeah.
What do you mean when you say local measurements? Some probability moments or correlation, something like that? Or?
Yeah, so if we're measuring temperature, we come in with a thermometer and it's making some measurement which is local in real space. Or if we're measuring correlation functions for that matter, we're measuring correlation functions of quantities which are local in real space, right? We don't generally make global measurements.
Thank you.
Okay. So, this talk is going to be mostly about settings in which this ergodic hypothesis is not true. So how can it not be true? Well, there's one class of exceptions, there's some classes of exceptions which are based on fine-tuning. So you could have some very specific set of equations of motion, where the ergodic hypothesis is not true. This can certainly be done, and this has been known for over 100 years. But I at least will claim that, to my mind, fine-tuned systems are not so interesting, because the moment you perturb the system even a little bit, then you would lose this very special feature. Yeah? Of course, you could cook up completely artificial sort of systems in which the ergodic hypothesis is not obeyed. I would say really the interesting question is whether you can get violations of the ergodic hypothesis which are in some sense robust. Yeah? And well, I said I'll talk about 2 examples. I doubt I will not talk about 2 examples. It's not going to happen. Maybe I'll get to talk about 1. It's okay. No, it's not a race. So the first example we'll talk about is something called many-body localization, which is something that happens in systems with strong disorder. So by strong disorder, imagine that the particles in question are moving in some very rugged potential energy landscape. Yeah, lots of tall mountains and deep valleys. And what happens here is that, look, the sort of toy classical understanding would just be to think that particles get trapped at the bottom of deep valleys and they can't escape. But actually it's more than that, because we're talking an isolated system. Energy has to be conserved. It cannot be created or destroyed. Yeah? It has to come from somewhere. If a particle goes uphill, it increases its energy. Where's the energy coming from? If it goes downhill, it loses energy. Where's the energy going to? In the context of an isolated system, neither is really possible. And with a very inhomogeneous potential energy landscape, what happens is that all of the excitations get trapped. They cannot move because moving would take them either uphill or downhill, and neither is compatible with conservation of energy. Yeah? So this was first pointed out for non-interacting systems by Anderson in 1958, for which he won the Nobel Prize. In the past couple of decades, we've come to believe it can happen even for sort of generic interacting many particle systems. Okay, now we could ask, like, how robust is this? Well, for starters, well, the answer is it's pretty robust. If you grant my premises of you have a perfectly isolated system with energy conservation, then you can perturb with pretty much anything that's short range in real space. And if you perturb with stuff that's short range in real space, then it's robust in a sense that can be made precise, but which I don't want to get into because it's like overly technical for the present setting. Okay, now why is this interesting? Well, one reason it's interesting is it's the first historical example of robust ergodicity breaking. And by now we know of others, but this is the first one we discovered. And it can support new sorts of phenomena without any analog in equilibrium systems. So it sort of illustrates the point that once you break the ergodic hypothesis, then essentially you throw out all the textbooks because all the textbooks assumed ergodicity was true, and now you're in terra incognita and you can have entirely new sorts of behavior. And I'll illustrate that with the idea of spontaneous symmetry breaking. Who here has seen spontaneous symmetry breaking before? Okay. Most of the audience hasn't. So I'll review the idea. So the idea behind spontaneous symmetry breaking is that, okay, what's an example of a symmetry? So it's typical that the laws of physics, for instance, have translation symmetry. Yeah? Meaning that they look the same here as 100 feet over in that direction, and they look the same in Chennai, and sort of you move from one point in space to another, and the laws of physics don't change. That's translation symmetry of the laws of physics. Yeah? So whatever underlying equations of motion we have, they can have some symmetries, and translation symmetry would be an example of a symmetry of the underlying equations of motion. The underlying equations of motion don't change depending on where you are in space. Yeah? That does not mean that the solutions don't change. Yeah? There is a particular solution to the underlying equations of motion, which is me. Yeah? And I'm here, I'm not over there. Yeah? So this solution is not invariant under translations. More generally, anytime you have a setup where the solutions to the equations of motion are not invariant under some symmetry transformation, where the underlying equations of motion are invariant, that's called spontaneous symmetry breaking. Yeah? And there's lots of lore on spontaneous symmetry breaking in statistical mechanics. The paradigmatic model that's used to describe it is called the Ising model. I suppose I should unpack this notation. So the idea behind the Ising model, so this is the simplest version of this, is that we have a collection of spins in one dimension. So you have spins on a line. Each spin you can think of as a little magnet, and it can point either up or down. That's it. Only two possibilities. It's a little arrow, a little magnet. This arrow either points up or it points down. And it's a whole connection of little arrows in the one-dimensional line, and they can point up or they can point down. And the underlying interactions of the system are such that energetically it's favorable to have all of the spins aligned. Yeah? If every spin is pointing in the same direction as its neighboring spin, that's good. If they're pointing against each other, that's bad. That costs energy. Yeah? So now you have, if you ask what's the lowest energy configuration of the system, there's two low energy configurations. One is every spin points up. The other is every spin points down. Yeah? Now, at the level of the underlying equations of motion, they don't care about whether the spins point up or down. Yeah? All they care about is that neighboring spins point in the same direction. They could be both up or both down, doesn't matter. Yeah? So if you take every spin in the system and you flip up to down to up everywhere in the system, that doesn't change anything for the equations of motion. Yeah? That's a symmetry of the equations of motion. The underlying equations of motion have a symmetry under flip every spin, up to down to up. Yeah? But the two low energy configurations, all up and all down, those are not invariant. If you take the all up configuration, you flip every spin, it becomes all down, it's different. Yeah? So this is an example of spontaneous symmetry breaking. You have a symmetry of the equations of motion. It's not a symmetry of the low energy solutions. Yeah? For this paradigmatic, one-dimensional Ising model, it's also known that the moment you go away from zero temperature, yeah, the solutions have the symmetry again. This phenomenon of spontaneous symmetry breaking is specific to absolute zero temperature. The moment you move away from absolute zero temperature, it goes away. And the reason it goes away is because at any non-zero temperature, the effects of entropy are sufficient to destroy this spontaneous symmetry breaking phenomenon. Yeah? And there's various ways in which you can quantify this in terms of correlation functions. There's theorems about lack of spontaneous symmetry breaking at non-zero temperature, in this context due to Landau and Peierls. Okay, this stuff is all in the textbooks. Now let's introduce disorder. Let's make the coefficients random. Let's introduce this random potential landscape. And immediately what happens is that now you get spontaneous symmetry breaking away from the ground state as well. You get spontaneous symmetry breaking at non-zero energy density. Yeah? So hang on. This is something which the textbooks claimed could not happen. Yeah? Where did the textbooks go wrong? Well, the textbook argument says that at any non-zero temperature, the effects of entropy will be sufficient to destroy spontaneous symmetry breaking. Yeah? This has an implicit assumption that there is such a thing as entropy. In order for entropy to be meaningful, you need the ergodic hypothesis to be true. If you make disorder strong, you break ergodicity, there is no entropy, and so this basic assumption which underpinned the textbooks falls apart, and now you can have this phenomenon which the textbook said was impossible. Yeah? So many other examples have been discovered since. The Ising example I gave you is the simplest and first. Most famous example is surely time crystals, but basic result is that there's new things that can happen once you break ergodicity, which could not happen if the ergodic hypothesis was true. Questions? Okay, so this was the first part of my talk. The second part of my talk I am not going to have time for, but maybe I'll just give you some outline. So now I showed you so far, I talked about one way to break ergodicity based on strong disorder. There's a completely different way of breaking ergodicity which we discovered recently that's inspired by the interplay of certain symmetries. I guess I won't talk about this. It gives a completely different kind of robust ergodicity breaking. Skip. It's fine. You can realize this in ultra-cold atoms, and it's been observed in various ultra-cold atomic contexts. Maybe just a summary. So there is an alternative route to ergodicity breaking that I did not tell you about today, but it exists. It goes by the name of Hilbert space fragmentation. Unlike localization, it does not rely on either disorder or energy conservation. Instead, it relies on having interplay of two symmetries plus spatial locality. Skip this. You could ask, can we do better still? Can we get stuff that's robust to arbitrary perturbations where we don't even need to demand spatial locality? And yes, we can also do that, but that's not only am I out of time, that's also out of scope. So I won't talk about that. Instead, I'll just move to my conclusions. So my conclusions are that, look, systems are complicated. Yeah, the world is complicated. The underlying laws of physics are relatively simple, but the world is complicated. And direct brute force solution of the underlying laws of physics is simply not practical, and even if it could be done, it would not be insightful. To actually get insight, needs new approaches, and those new approaches is what statistical physics aims to provide. It aims to bridge the gap between underlying equations of motion and actual understanding of macroscopic systems and emergent phenomena. Now, statistical physics is a well-developed discipline, but it's a discipline that makes certain assumptions, and one prominent assumption among those is the assumption of ergodicity. Yeah? If that ergodic hypothesis is false, then you are in here there be dragons territory, where you can get entirely new sorts of phenomena, which stuff that the textbooks say is impossible or even did not anticipate. Okay, we can, in fact, robustly break ergodicity in quantum dynamics. I talked about one way to do it. I also at least mentioned that there was at least one more, which I didn't talk about. I skipped all the slides because we didn't have time. And now we know there's even better ways, which are too complicated to put on slides for this talk. But we have a rapidly developing understanding, let's say, of how to violate ergodicity in quantum dynamics. Traditional statistical physics assumed this. Now we can break it, we can construct systems that break ergodicity in the laboratory, and these systems represent an exciting new frontier for statistical physics. Okay, I should say that this has been based on work that I've been doing over the last 10 years with a large number of people. I think 4 deserve special mention. So this is Shivaji Sondhi at Oxford, this is David Hughes at Princeton, Vedika Khemani at Stanford, and Andy Lucas, my colleague at Boulder. With that, I'll also advertise my Coursera course again if you wanted more details on the sorts of things that I talked about today, if you think many-body physics is interesting. And with that, I'm happy to take more questions.
Thank you, Rahul. Okay, more questions. Okay.
What will be the culmination of your study? Where your study will end up? What the end result of all your?
Well, I would say, for now, we're still in the exploratory phase of understanding what's even possible, right? So there's this well-developed framework for equilibrium statistical physics, yeah? And I would not go so far as to say that we understand everything in equilibrium, but there's a pretty good framework for understanding what's possible and what's not possible. When you move to the out of equilibrium setting, we don't even know what's possible and what's not possible. Yeah? So step 1 would be some sort of understanding of what's even possible in an out of equilibrium setting. Yeah? Once we understand what's possible, then we could have some more fine-grained sort of classification, characterization. Now, the ultimate aim would be to have a theory of non-equilibrium statistical physics, which is as powerful and predictive as the equilibrium statistical mechanics that was formulated, in the 19th century, at the dawn of the Industrial Revolution. But we're quite far from that.
Hey, sir. So, in classical physics, we have concepts like observer or frame of reference, right?
Yeah.
But then when it comes to, we can say any general reference, but when it comes to quantum mechanics, is it extrapolatable, or is there anything similar or analogous to something that I can take as a reference, or say an absolute value or a relative value kind of thing?
So, we could make the question precise. So when you're talking about frames of reference, you're talking about things like Galilean transformations, where you sort of boost to a frame that's moving at a certain velocity. That's what you have in mind?
Yeah, exactly.
Okay. So, Schrödinger quantum mechanics is Galilean invariant, but it's not Lorentz invariant, meaning Lorentz transformations would be special relativity. So standard quantum mechanics is not special relativistically complete. In principle, we know how to fix that. So if you move from quantum mechanics to quantum field theory, now you could write down field theories which are Lorentz invariant, and they would be invariant under Lorentz boost, so they would be special relativistically complete. It makes things more complicated, and there usually isn't any real payoff for doing this, because you're doing experiments in some quantum mechanical system, there's an obvious lab frame. And why not just work in the obvious lab frame? Why demand that you have either, that you have some Lorentz invariant description?
Thank you.
Hello, sir. One small question regarding the information in the systems from the early beginning. I've stuck there. So you have told that when the milk is added to a coffee cup, the particles move and they go to a equilibrium state where they lose some information, and we cannot evolve the system backward because we cannot measure the system very precisely. Even if there is a small mistake in the measurement of position and the velocity, we would miss the initial position.
Yep.
And the same thing which also is applicable for quantum systems, wherein we cannot measure the position and velocity or momentum at the same time. In this case of coffee cup or a classical system, we are losing some information and the information is destroyed. But you told that the information is preserved in a quantum system. Why is this a case? Like in a quantum system also I'm unable to measure, in a classical system also I'm unable to measure, and the information is destroyed in one.
So, I mean, as a matter of principle, the information should always be there in both the classical and the quantum system, right? Because our ability to measure perfectly, that's an artifact of how good we are as experimentalists. Now, if you actually try to run the time evolution backwards, in a classical system, you would have one set of problems, which is that your equations of motion would be nonlinear and subject to chaos, and so you wouldn't be able to extrapolate backwards. Yeah, that particular resolution doesn't work in quantum mechanics because Schrödinger's equation is linear. But you have a different resolution, which is that the space of all possible measurements is much vaster in quantum mechanics, and the subset of measurements that you can actually make is much smaller, relative to what you would need to be able to measure to completely characterize the system. So it's just a different resolution, but it's different in detail, although maybe not so different in spirit.
Okay. Thank you.
So, is it true that in most cases where we see ergodicity breaking, it's due to like a rugged potential energy landscape, or are there other cases where we can see this?
There are definitely other cases. The rugged potential landscape is just the only one that I talked about or had time to talk about. Now, the second example, which I skipped because of time, no disorder, no rugged potential landscape.
So in that case, what causes the ergodicity breaking?
Yeah, it's the interplay of two conservation laws.
Sir, could you please explain about phase space?
About phase space. What do you want me to say about phase space?
Any general information about phase space and thermodynamic probability of distribution?
In the idea of phase space is that you have positions and momenta,
okay.
And phase space is the space of positions and momenta.
Okay.
I don't know what more to say. That's what phase space is. But, yeah.
Okay, thank you.
Yeah.
So the references which have been mentioned in the PPT, they are all post 2010, or other than the mention of Ising, Model, and Anderson. So has there been a recent breakthrough in past decade of our understanding about it, or is it's just we are mentioning the latest work?
No, I think so. There's really been almost everything I said is post 2010,
okay.
And I think sort of all the interesting developments in this field are last 15 years.
Okay. So if we read old classics like Lieb and Uffing, we won't find this kind of stuff,
correct,
or it's theoretically been predicted, just that we are observing it now.
No, I think even the theoretical predictions are new.
Okay.
Obviously, I'm not saying nothing was known prior to 2010. There certainly are some precursors, and maybe if you read some of the old classics, with a lover's eye, you could say that maybe the heroes of the past might not have been so surprised by some of the new developments. Maybe they might have at least implicitly anticipated some of this, but it's certainly not explicitly there.
Professor, can you please explain how having a higher dimensional symmetry, as you stated, the fractonic symmetries can also play a role, how they actually break the ergodicity hypothesis, although it was not a part of the...
Can I take 10 minutes to answer that question? Okay, so let's go back. So let's consider a specific... I had slides on this. Let's consider a specific example. So the specific example we'll consider is a system with two conservation laws. And the two conservation laws that I'll consider are charge conservation and dipole conservation. Yeah. So charge conservation is the usual notion of charge. You have a single charge, it cannot be created or destroyed. By dipole conservation, I'm defining dipole moment in the obvious intuitive way. It's just the position weighted charge. Yeah? What's the implication of this? If you have a single charge, it cannot move, because if a single charge hops either right or left, it changes the dipole moment of the state. Yeah? If you have a plus charge and a minus charge next to each other, a dipole, that can move freely. Or if you have two charges, they can move in correlated fashion without changing their dipole moment. Yeah? So single charge cannot move, two charges can move in correlated fashion, plus charge and minus charge can move freely. Yeah? Now we want to look at the subsequent dynamics. If you do this, you observe empirically that it's non-ergodic. So this was originally a sort of empirical numerical observation. It's non-ergodic. Why is it non-ergodic? Well, it turns out there's actually a very nice, simple explanation. Consider some system where the charge pattern alternates between regions which are all plus and all minus, yeah? With the domain boundaries which separate all plus and all minus regions being at least a minimum distance apart. Let's call that minimum distance m. Yeah? And let's suppose that the dynamics is locally generated on the scale m. So my dynamics is generated by some underlying equations of motion which are local on the scale m. There's nothing that acts more long range than m. Yeah? So now I come in and I try and do my dynamics, and I act always across either 0 domain walls or 1 domain wall. I can never act across 2 domain walls because they're too far apart. If I act across 0 domain walls, I'm acting on a region that's locally extremal charge. There's nothing you can do to that consistent with charge conservation. I think you can't delete plus charge. If you act across 1 domain wall, we're acting across a region that's locally extremal dipole, because if you shuffle plus and minus charges, that will change the dipole moment, because all the plus charges were to the right, let's say, and all the minus charges to the left. Again, nothing you can do to that. So any kind of pattern like this, it just cannot change under any dynamics with these two conservation laws and locality. If you ask how many patterns like this can I write down, you can get an exact count, but it's sort of simple. Exact count is complicated. It's simple to place a lower bound. So to place a lower bound, you say you take the system of size big L, you carve it up into blocks of size little m. Each block you can freely allow to be either all plus or all minus. That will satisfy this condition that it's a complete vegetable under the dynamics, so it just cannot change. And there's at least 2 to the power L over m states of this type, exponentially many in system size. And you can generalize this argument to d dimensions. So if you're in d dimensions and you conserve charge and all d components of dipole moment, then you'll have sort of exponential in system volume number of states, which just simply cannot change under any dynamics which is spatially local on a given scale and has these two conservation laws. Okay?
More questions from here? Okay. Yeah.
Is there so with ergodicity breaking, is there some sort of probability function that is associated with the dynamics of this exploration of microstates in this case? And if so, what does that typically look like?
Yeah, so in the context of a system which breaks ergodicity, it's not really meaningful. I mean, the concept of you have some probability distribution over microstates, it's sensible if the system can actually explore different microstates. Yeah. If it cannot, then what does this probability distribution even mean? There is just the state in which it was prepared.
Sir, can you tell us something about metallic glasses? Does it have the same property or?
So you're thinking of, for example, you have some metal and you have some magnetic impurities. Yeah. And then you have some glossy behavior of those magnetic impurities in a metal. Now, so I think to zeroth order, that's disconnected to what I'm talking about. That's a sort of a separate topic. No, it's similar in the sense that if you're talking some kind of glass, then you're also talking some kind of non-ergodic system, but it's not the same kind of non-ergodic system that I was talking about today.
Are there more questions? There are several questions from people online. Let me just read out two and slightly modify them as I understand. The first one is, is there a tabletop experiment on a quantum system that displays ergodicity breaking?
Is there an example of an experimental quantum system?
A tabletop experiment.
Yeah, sure.
Yeah.
So for this method, this charge and dipole method, one classic example is cold atoms in a tilted optical lattice. So if you have cold atoms in an optical lattice, then atom number is charge. You tilt the optical lattice, center of mass couples to the tilt, center of mass is dipole moment, center of mass cannot slide uphill or downhill. That would change the dipole moment. So there you have charge and dipole moment conservation, and you have this kind of ergodicity breaking, and it's been seen by multiple different groups now in this context. That's one concrete example.
The other is ergodicity breaking and loss of information related?
Yeah, they're related in the sense that if ergodicity is broken, so glasses of the sort that I was talking about today, they have the property that they preserve memory of the initial condition in local observables out to infinite times. Yeah, so you don't get loss of information about the initial condition.
Okay. Are there further questions? If not, let's thank Rahul for the interesting talk once more. See you all at the next Coffee with Curiosity talk. Thank you. Want to say something?
Yeah, thank you. Thank you all for coming here.